In our trig journey, we're going to look now at simplifying combinations of a cos x plus b sine x into simpler forms. So we start with something like this, and we usually end up with something just with only sine or only cosine in it. We don't have both cos and sine in it. Okay, that has various advantages when we do things like we want to sketch it or solve real life problems. So there are advantages to going through with this. So it does have purposes, but this video is not so much about the purposes, it's about where these equations and rules come from. So let's have a look at that, and after that we'll do a straightforward example. So before we get into the examples, we can see that in the first instance here, a cos x plus b sine x can be shown to equal some r cos x minus alpha, where alpha is an angle. Now r is defined as the square root of a squared plus b squared, and cos alpha is a over r, sine alpha is b over r. It is also possible to convert a cos x plus b sine x into r sine x plus beta. So it's x plus this time and some other angle beta. So again, r is the square root of a squared plus b squared. Sine beta is a over r and cos beta is b over r. Do you see the similarities there? So those are important to note. It's interesting that cos alpha and sine beta are equal, and it's interesting that sine alpha and cos beta are equal in their result. Note that these things are not on our formula sheet. So proving where this comes from, we've got, if we let r equal square root of a squared plus b squared, and we consider the point P, if that point P has coordinates a on r, b on r, its distance from origin, O, so from O out to P, all squared, would be, using a triangle and a diagram, we could show that it's a over r squared plus b over r squared, Pythagoras' theorem, using a right angle. Using index laws, we can show that it's equal to a squared over a squared plus b squared, because r squared is the same as a squared plus b squared. If you pause and have a look, you'll see that. Plus b squared over a squared plus b squared, common denominator, so we've got a squared plus b squared over the same denominator, and that equals 1. That means we're talking about a unit circle, so P is on the unit circle. So thus there exists an angle alpha such that a over r is cos alpha and b over r is sine alpha. So we can write a cos x plus b sine x equals r outside of a on r cos x plus b on r sine x. If you're a bit lost, the r's will cancel out. Okay, so there's an r on the outside which will cancel with the r in the denominator, and you'll get what's on the left hand side of the equal sign there. Okay, so just stay with me, and what that does is that we can write r outside of cos alpha, because we can replace a over r with cos alpha, cos x. We can replace then b on r with sine alpha, sine x, which is r cos x minus alpha if we use one of our identities. The identity is this one here, number 2. We have cos A cos B plus sine A sine B is cos A minus B. Hence we have here r cos x minus alpha, where we've got A is x and B is alpha. Now I'm not asking for you to be able to repeat that or regurgitate it, but that's where it comes from, and you could similarly find the same one for when we have, I won't show it here in the video to keep the length down. Similarly, we could show the other one, which is when we've got the same a cos x plus b sine x, and in the case where that equals r sine x plus beta. Alright, so again, you don't have to show this. This is where it comes from. Let's finish the video off with an example now. So as an example, if we're given 3 sine x plus 5 cos x, convert it to the form a sine x plus theta and sketch it in the interval 0 to 2 pi. So we're going to end up with just a sine graph from that combined graph given. So remember that we've got, in the case to convert here, we've got the second situation there. Okay, so a cos x plus b sine x is r sine x plus b, where we've got r and beta defined as such there. Okay, so I started the ball rolling by putting the rule there, and then r is 34 because we have a is 3 and b is 5, putting that into the formula, and then sine b beta is a over r, which in this case will be 3 over 34. Cos beta equals b over r, which will be 5 over 34. Now this one's a bit icky because there's no exact values happening there. Oh my gosh, I've just realised something. Square root of 34, that is. Woo. Sorry. And that's about 5.83 if you like decimal approximations. So, yes, sorry. Got to take the square root, haven't I? Okay, so try that again. So let's go, it doesn't matter which one you go. You can even use tan if you want, but beta is the inverse sine of 3 over square root of 34. Let's try that. I've spotted another little error. Whoops. Now it's, look at the form carefully. It's a cos x, b sine x. So a would actually be equal to 5 a cos x, and b equals 3. So I've got to amend that on mine, and I need to be a bit more careful because it gave me the function in a reverse order with that little sum there. So luckily I've spotted that before I went too far. There we go. So it doesn't matter which one you use, inverse sine or inverse cos. Let's use inverse sine 5 over the square root of 34. You could even go sine on cos being 10 and use inverse 10. That's fine too, if you want to dodge the square root of 34 situation there. And we get 1.03 radians. Now that's only going to be an approximation because it doesn't align with exact values, but they often do align with exact values. So, and then we can formulate that as a function. So that means that the function given, which was 3 sine x plus 5 cos x, is now in the form. So 3 sine x plus 5 cos x equals square root of 34, or about 5.83, root 34 sine x plus 1.03, and we can plot that, which I'll do quickly because that's not the focus, but you use your existing techniques for graphing, and we would find that it's got an amplitude of root 34, about 5.83. You'd have to go in and you'll have to see another video for the specifics of it, but you need to look at the A, and we've got a phase shift of 1.03 radians, which will be to the left. Okay, so that means when it would normally go through pi, it goes through pi, take 1.03 radians. So sine, as you know, sine of pi is 0. Okay, so the standard sine wave would go through there, but this one's been phase shifted there, so it'll go through about 2.11. Correspondingly, the maxes and the mins and the other zeros get moved. So you need to do proper curve sketching process if it needed to be justified.